Basically, we have a long piece of text, a corpus, and from that corpus, we want to say something. And using that piece of text, using that piece of speech, we want to find the corresponding part in the text. And we want it to be fuzzy, so it's not going to be 100% exact. So if you're kind of remember a quote from the book and you want to find that quote in the book and the quote is not really accurate, the case might not match. Also, could be uppercase, lowercase, special characters, but also some words might not match. Still gonna be able to find it. So the libraries that I need, first from FuzzySearch, which we just installed, I'm gonna import find near matches, which is gonna do approximate matching. And from Faster Whisper, which we installed, I'm going to import a whisper model. Okay, so the whisper model will turn our audio file into transcripts, but not the whole audio file. The whole audio file is relatively large. In this case, it is around 1 hour. So we don't want to transcribe the whole thing. If you think of it as a human being, if you want to find this piece of audio in this large corpus, what you'll basically do is to listen to the initial segment of the audio and also the final segment of the audio and try to find the beginning and end boundaries and then cut there. So that's what we're gonna do. We're gonna, let's also import. So I'll just go ahead and import from Faster Whisper, just to make things easier. It has an audio.py, so I'm going to import the decode audio. This is gonna load audios from the disk and we can slice into it. So first I need the start, let's call it audio. I need to define this and also the end audio as well. So let's find these two parts. So if I load the whole audio first, I would call the decode audio, which I just imported. It'll ask for the input file. The target sampling rate by default is 16,000. This is the sampling rate that Whisper model was trained on. So we're going to keep it as it is. You have the option to split stereo channels into 2 channels. And we don't want to do that. We want to maybe downsample it into mono. Okay, so I'll just give it the audio path here. So let me just go ahead and copy paste chapter 8 combined.wave. And it should give me the audio as a numpy array. Okay, so my audio is a numpy array. Let's check the shape to see if everything checks out. We have this many samples here. If you divide it by the sampling rate, 16,000, you get that it's 3,688 seconds, which is 1 hour plus some change. Okay, so now I need to create these 2 segments. So let's do it. So start audio is my original audio file. I'm going to slice to maybe the first chunk. So I'll set a chunk size. So I would say maybe 100 seconds. So it is in seconds. If I want 100 seconds in the start of the audio, we'll say slice up to 100, but this is in terms of samples. So to convert to samples, we'll multiply by the sampling rate, 16,000. So I'll replace the 100 to chunk size, so maybe we can change it later if the chunk is too small or too big. I'll do the same thing, so slice the audio to find the end segment. So we want the final 100 seconds all the way to the end. So let's start with negative chunk size times sampling rate all the way to the end. So this should give me 2 chunks whose shape would match. So shape for the start audio, shape for the end audio. Let's have a look. Both are matching size, 100 seconds. Okay, the next step is to transcribe the start audio part. So the start audio will sound something like this. Chapter 5, blah, blah, blah. Let's see.
Chapter 5, Sigmund Freud.
Okay, Chapter 5, Sigmund Freud, etc. Okay, so now to turn this piece of audio into text, we're going to use our Whisper model. So I'll just instantiate the Whisper model. We have to set some parameters here. First is the model size. Of course, you can choose large version 3, which is extremely accurate, but it's going to consume a lot of memory. For this example, I'll just go ahead with the tiny version, which is really lightweight and you can run it on CPU with good speed. Compute type is also an important argument here. You can set it to flow 32 or 16 if your GPU supports it. That's going to be accurate. I'm going to use int 8. It is really lightweight. And at the same time, it just gives you a performance boost at the cost of a little bit of accuracy. Do we need anything else? Not really. So I'll get back my model. Let me see if it gives it a tuple or not. Faster Whisper model. No, we're good to go. So the model has now this transcribe method. where you can give it a segment of an audio, could be a string from your disk, file path, binary IO that you can read in real time using maybe your microphone and transcribe in real time, or a NumPy array. Here we have a NumPy array. So I'm going to pass that. So let's do transcription for the start audio. And we can set some parameters here as well. You can pass the language if you know a priori what your language is. In my case, the base language is English, even though we have some German segments in it as well. The generation hyperparameters seem good, the default. Word timestamps is false, without timestamps is false. What it means is that it's going to give you the timestamp of each segment. If you set the word timestamps to true, it's going to give you word level timestamps, which is good for creating videos highlighting each word as being spoken. We don't need any of these. It's going to take longer because it has to do speech alignment in addition to transcription. So we're going to set them as false. And the output would be, let's call it the segments. And I believe it's going to give you some metadata as well. So I'm just going to ignore that. And let's just transcribe the start audio. So it gives you a generator object. And right now it's not done any transcription yet. To get the transcription, you have to write a for loop and go through the generator, get each segment one at a time. So I can go for seg in segments and just print it to have a look at what it has. So let's just print every segment for now. Okay, this is the first segment, second segment, and so on. You can see it's a segment object. It's like a custom Python object. What it does have, each segment has this text key, which is the transcription. So what I'm going to do instead is I'm going to create an empty list. I'll call it the start segments. It's an empty list. And I'm going to append to the start segment each segment's text. I believe I cannot index into it, so I just call text on it. Let's see if we do this, what will happen. So right now, since we read through the segments once, the generator is now empty, so I have to call this again and now call the segment. Okay, let's see. So now this is the start segment. The first 100 seconds of the audio, this is the first segment that was spoken. Second, third, all the way to the last. So it says chapter 5, Sigmund Freud. In the actual book, if you remember, we had a different piece of string. Instead of chapter 5, we had, so it doesn't map exactly from the transcription into the actual book. It's V, Sigmund Freud. Also doesn't map 101. It is Sigmund Freud 1. I embarked on the adventure of my intellectual development. Embarked is also all caps, development. So let's find the starting segment in the book. To do it, we'll use the FuzzySearch that we imported here. Find near matches. And this is a really handy function because in find near matches, I can pass in a subsequence or a query, which in this case would be maybe the first sentence of my audio file. And then a sequence, which will be the whole book, all the 1,000 pages of the book. And then I have to specify some parameters here, which we'll explore later. So here I'll just start with saying my start segment would be just the first sentence. So start with the, let's call it string would be the start segment, maybe just the first one, just the first sentence. Trying to find the first sentence in the audio file. We might want to increase it a bit. Maybe if we cannot find the first sentence, there's a lot of noise, a lot of things that do not match. We might want to combine the first two, first three, first four. So I'll just make it customizable. So I'll just join these results without any space because a whisper already puts a space in the beginning of the sentence. So this is what it's going to look like. Chapter 5, first sentence, second segment. I'll start with the first. So I can put it as a segment size. Segment size as a parameter we can set. So segment size, for now it's 1. Okay, so let's find this part from ASR, start string in the book. So before we do anything else, we need to find the book, open the book. To open the book, I'll just write a simple open function with context manager. So with open, the name of the book is cg.txt. Let me triple check. Yeah, cg.txt. We have a lot of crazy encoding going on, so I think the best bet would be to use UTF-8 as F, and let's call the variable book. So book would be reading the whole text file. we can just display to see what's going on inside. And this is the whole book. So let's see how big the book is. 899 plus, around 900,000 characters. So first let me use the match, like a simple book find. You can use the Python's find method where the substring is found in the book. So the substring here would be our query or the start string. So let me see if I can find this exact string in my book. So let's go find. It's -1. It didn't find anything. That's why we need to use FuzzySearch. So we know it's not exactly in the book, this exact phrase. It's approximately in the book. So I'll pass the book as the sequence. Then I need to set max substitution, insertions, deletions, or L distance. This will tell me, or I will tell the FuzzySearch, if you don't find this exact phrase, which you'll probably not find it here, how many substitutions, how many modifications and edits you need to do in order to find this string in our book. So let's try this out before we run it for the whole book. Let's just try this out for a simple example. So if I have this piece of string, let's say Sigmund Freud, and I want to find Sigmund, and let's say I put the max ldist to 0, meaning no modifications at all, it's able to find it. It says Sigmund is in this string and the index is from 0 to 7, the beginning and the 7th character. If I change it a bit, maybe I forgot to put a U there. There's a typo. Sigmund in this string without any modifications is gonna give me an empty list. It didn't find anything. But how many edits do we need to do to make this match this? One character edit. So if I set L1 distance as, or set the L distance as 1, now it's gonna find it. But again, if I remove more characters, so now 2, maybe 3, it's still not gonna find it. So I have to increase it even more. Now here's the issue. The bigger this is, if they find 20 matches, the longer the computation is going to take. So we have to be really careful with the max L distance. If the substring that we're trying to match in the book is really different, in this case it actually is, we have maybe 3, 4, 5, 6, 8 characters here that don't match. You have one more here. So the max dist probably has to be 10 or 12, and that's gonna take a long time to find it. So we have to be really careful with this parameter. Well, you see how this works. So if I go ahead and try to find near matches of this substring inside my book by setting the max L distance to, let's set it to maybe 2 this time, it's still gonna be empty. We already know we have to remove this part. So maybe 10, it's not going to find it. Maybe 20, now it's trying to make 20 substitutions, so it's gonna take a long time. Let's see if it finds anything. It's not able to find anything even now. So maybe 30. So what I'm doing right now, if I want to generalize and automate it for future tasks, it's basically a while loop. So if I get the output, call it M matches, because it's a starting match, I'll just put the SM for the start match. And when it doesn't find anything, so in this case, let's put it to 1. And if you run this, SM would be an empty list. So I can say while SM, or the length of SM, is 0, aka it's an empty list, do something, which is, let's set the max L distance initially to 1, which is pretty fast and should work for most examples. Most examples have 101 or maybe 1 modification distance from the audio to the book. But then if you do not find any matches, go ahead and increase the max L distance by 1, run the search again. If it doesn't find anything, keep adding to it until you find it, and then stop. So first I have to declare SM as an empty list so that the first iteration would work. So let's start with 1, increase it. I'll just, for the sake of example, display what's happening here. So if it doesn't find it, say, so the max L dist didn't find anything, increasing. Okay, let's see how many iterations we need. 14 doesn't work either. Now there's this possibility that we do all these substitutions here near Sigmund Freud, but if you look, I embarked on the adventure. There's kind of unnecessary mismatches, which is the starting string has some words as capital, the book has some other words as caps. So what you can do, a simple fix that will make the text in both cases much more similar is to make them lowercase. So if I do this, I'm now comparing this lowercase to the actual book in lowercase. That should save us much more computation. Okay, let's see if it is able to find anything. So you see we get kind of exponentially slower as we increase the value of max ldist, but it eventually found it. So found the match, which is our SM variable. It has this start, which is the start index. It's a list, so I have to pick the first one, the best one. It's this part. So if I index into the book, I can index to the book using the start all the way to the end. Okay, so the first part of the book, chapter 5, Sigmund Freud, I embark on the adventure of my intellectual development. It found it in the book. It's V, Roman 5, plus a bunch of new line characters. That's why we need to go to 16. Sigmund Freud 1, a bunch of new line characters. I embark on the adventure of my intellectual development. So we found the beginning after some time. So we can do the same thing basically for the end part. I'll just copy paste as much as I can. Let me merge these cells because we need to reuse them a lot. We need the segment size. Maybe open the book a bit earlier. Okay, so now let's go ahead and transcribe the end audio. So this would be the end of the book. Get the segments, put them in the new list called end segments. So for segment in segments, append the text to the end segments, and then join the end segments segment size, which is 1 for the time being, and try to find it. So let's transcribe it using Whisper. I forgot to call this end string, so let me fix it again. End string, one more time. Okay, so the final sentence is patience. He saw with patient's eyes, so to speak, and so reached a deeper understanding. Let me check to see how close and accurate this is. So this is probably the final sentence in our audio file.
Such an enterprise entailed the impetus which he gave to our civilization, despite the fact the assimilation of the fundamental insight that psychic life has two poles still remains a task for the future.
I made a mistake here, apparently. This is the end segment, so I have to go segment size minus all the way to the end to get the final sentence, or if it segment size is 2, the last 2 sentences. So I'll just run this part again. So that psychic life has 2 pearls still remain a task for the future. Let's see.
Still remains a task that psychic life has 2 poles still remains a task for the future.
Okay, has 2 pearls. I'm not sure if it's correct, pearl or another word, but I'm going to, using FuzzySearch, find this sentence in the book, which is our final sentence for that audio segment. So lowercase of the end string, find it in the book, call it an E match or end match, and see how many tries we need. 5, and it found the start and the end. Psychic life has 2 poles. Okay, poles still remain a task for the future. So it had to fix the poles and pearl, match them. Very good, very powerful. So I'll just get the final segment. I have the initial segment of the book, which is SM start of the first sentence of the audio file. And then EM, which is the end of the audio file, the final sentence. I will pick the ending index. And this should give me chapter 5, Sigmund Freud, all the way, all the piece of text until this assimilation of fundamental insight, task for the future. So I'm just going to copy paste this chunk inside a Python script. Let's call it audio in book. So we're going to import all the libraries that we did. It's going to take a segment size, chunk size that we saw, audio file, book file or text file, model size by default tiny, and it's basically going to do what we did in the notebook in a script, increase the L distance, find the starting and end segments, and write the result after it finds it in a text file. So now really it's going to speed up creation of SRT and subtitle files. So I'm just going to try it out here. I put it in my path, so I just can call find audio in book. Then I'll need to pass in the name of the audio file, which is chapter 8, wave, path in the name of the text file, cg.text, and I can do a search. Okay, it's trying to find the start segment found, just like we did in the notebook, end segment found, and here we have the text file of the chapter from start to finish that corresponds to this audio file. from a massive book. So the next step would be to generate the subtitles using this exact piece of text, and that's called forced alignments, and I'll do it in a different separate video. Thank you very much.